There are three basic transformations that we're going to cover today. Here they are. We're going to cover reflections, rotations, and translations. You've done these before. You did these back in elementary maths. A reflection, you've got a mirror image. Okay? A rotation, that's kind of like having a leash tied to something and you're spinning it around a pivot point. A translation is as you're moving something. So you've got a reflection is a flip. You want to write this. A flip, a rotation is a spin, and a translation is a slide. Something else to point out. So therefore, when you're doing a reflection, you're going to have a line. Some sort of line that you're reflecting across. Kind of like your mirror. Anytime you're doing a reflection, a rotation, you're going to have a point, a pivot point. And like think about again, a dog on a leash. That spike where, let's say you got a spike drove in the ground to keep that dog in place. It's got that pivot point. That spike that the leash is tied to would be that pivot point. And then a translation, you're going to have some rules about where are we going to slide that to. The previous three transformations are called isometries. An isometry is a transformation that preserves length. What that means is after the transformation has happened, is the figure the same size as it was before? Yes. If you spin it around a pivot point, it's still the same size. The side lengths are the same. When you move it, still the same. Or if you rotate it or flip it, the side lengths are the same. Isometries also preserve angle measures, parallel lines, distances between points. Transformations that are isometries are called rigid transformations. You don't really have to know that. But what I would put is when you have an isometry, same size and shape. The shape does not change. The size does not change. Everything about the shape is the same. It's just in a different place. Okay. Now, we're not going to do them this year. You might talk about them in some of your other math classes. A dilation. I think it's an O there. Does anybody know what a dilation is? When you perform a dilation on a shape, what does it do to the shape? Or when you perform a dilation on your eyes, what does it do to your eyes? It shrinks it. And a dilation would be either a shrink or a stretch. So is a dilation an isometry? No. Because you don't have the same, you have the same shape, but you don't have the same size. You shrunk it, you stretched it, and a dilation is not an isometry. Reflections. It says a reflection, and y'all don't have to write all this down. A reflection in a line maps a point to its image such that if the point is on the line, okay, let's talk about the reflections. Again, when you're performing a reflection, it's going to pretty much preserve distance. Let's say you want to reflect that point across the line. The biggest thing to remember is distance is preserved. If this is A, okay, reflected across the line, let's say that's 3 inches away, well, its reflection will also be 3 inches away, A prime. Something else that we need to know, your original image is called a pre-image. What you start with is your pre-image, and after you perform a transformation, that is simply your image. You have a pre-image and an image. And what this is saying here, it's kind of common sense, is if the point does not lie on the line is the perpendicular bisector of the segment joining the 2 points. If the distance from here to here, and again, distance is perpendicular, would be the same thing as the distance from here to here. That's all this is saying. But what if we want to reflect the point and it's right here? Let's say that that's A. And what's A prime going to look like? Same thing. Put your nose against the mirror, right? That's what it's doing there. What if the image is, or the pre-image is on the mirror, then the image is going to be on the mirror. So that's reflection. here's your rules for reflections. This is what I want you to write on your note cards. For a reflection, if you want to reflect across, or they call it in the x-axis, reflection in the x-axis, here's your rule. XY changes into x negative y. And in the y-axis, your rule is xy turns into negative xy. So as you're finished writing these down, if you want to reflect something across the x-axis, look at this first rule. XY turns into, that's what that arrow means, XY turns into X negative Y. So the X's stay the same. If you want to reflect a point across the X-axis, the X's stay the same. The Y changes from positive to negative or from negative to positive, the opposite of Y. Here's some examples. 4, 1, reflected across the X-axis becomes 4, negative 1. 7, 3, when reflected across the X-axis, turns into 7, negative 3, and you can see that. Or you could say 7, negative 3, if you reflect it, would turn into 7, positive 3, the opposite of Y. Same thing with the y-axis. Negative 2, 3 turns into positive 2, 3. XY turns into the opposite of X, comma Y. Negative 6, negative 4 turns into positive 6, negative 4. That reflects it across the y-axis. Let's do some more. Graph each figure and its image. And a lot of people get mixed up with that whole image thing because you would think there's an image would be what you're given. You're given a pre-image, and we're going to turn it into the image of it. The pre-image is what you start with. After you transform it, it's now an image. So it says graph the figure. I already done it for you. Here's triangle ABC with vertices negative 5, positive 3, 2, 0, and 1, 2. And we want to reflect it in the x-axis or across the x-axis. And that's the reason I put my dotted line here. Here's the x-axis. So negative 5, using that rule, everybody look at the rule says x comma y turns into what? In the x-axis? X negative y. There's the rule. So negative 5, 3, 2, 0, and 1, 2 will turn into, help me out, Brianna, performing that rule. Negative 5, comma 3 will turn into what? Negative 5, negative 3. Let's plot that. Negative 5, positive 3 turns into negative 5, negative 3. Do you see how it reflects? 2, 0, Claudia. What does 2, 0 turn into? 2, 0. Can't take the negative of 0. You see that person has their nose against the mirror. It's on the mirror. That's the reason it doesn't flip. That's the reason it doesn't reflect. And Destiny 1, 2 turns into perfect. So 1, 2 turns into 1, negative 2 with connector dots. And you have reflected that whole shape across the x-axis. What used to be up here is now reflected. Again, this is called a pre-image. And this is your new image. Okay, next one. It says graph the figure and its image under the given reflection. We have parallelogram PQRS with these vertices, negative 4, 1. 2, 3, 2, negative 1, and negative 4, negative 3. And we want to reflect this in the y-axis, or across the y-axis. Sydney, look on your rules there and tell me, how do I reflect something across the y-axis? We're going to turn xy into what? Negative xy. So let's go down and let's perform all these transformations. Stephen, negative 4 to 1. When you apply this, xy turns into the opposite of xy. Negative 4 to 1, Stephen, will turn into what? turns into x turns into the opposite of x. So positive 4, 1. Good job. If it's negative already, it's negative, negative now. It's positive. So negative 4, 1 turned into positive 4, 1, which is 1, 2, 3, 4. Hang on. Negative 4, 1 turns into, yeah. We can do a different color. 1, 2, 3, 4, 1. So this point reflected over to here. Positive 4, 1. The second one, 2, 3, Jackie. What's 2, 3 going to reflect to? Perfect. Negative 2, 1, 2, 3. This point went to here. Zoe, 2, negative 1 will turn into? Perfect. Negative 2, negative 1. This point to here. And finally, Hunter, the last one, negative 4, negative 3 turns into 4, negative 3, which is 1, 2, 3, 4, 1, 2, 3. Connect our dots. It was a parallelogram before, it's still a parallelogram, but it reflected across the y-axis. To reflect something across the line, y equals x. When we get to algebra 2 pre-calculus, the reason this whole line y equals x is pretty important to us is when we're dealing with inverses. We'll talk about that later, but inverses come into play when we're talking about this y equals x line. Here's your rule. Reflection in y equals x would be xy turns into yx. So we see here a couple of points. Negative 1, 4 turns into 4, negative 1. That's a reflection. The line, let's talk about y equals x before we talk about anything else. The line y equals x. We did slope-intercept form and all that stuff when we first started, bless you. When we first started this chapter, y equals x is in slope-intercept form. What's its slope? 1. Good. Does everybody say that? 1 over 1. Rise 1, run 1, rise 1, run 1. What's its y-intercept? 0. And I think we talked a little bit about y equals x. If you have a y-intercept of 0 and you rise 1, run 1, rise 1, run 1, rise 1, run 1, does everybody understand this? X and y-axis, those are two perpendicular. The x and y-axis form perpendicular lines. Well, if you drew this line y equals x, you're rising 1, running 1, rising 1, running 1. You're running and rising the same amount. You remember how big that angle was? 45. It splits that x and y-axis. The line y equals x is a perfect split between that x and y-axis. So that's what we're reflecting across, and it's really easy. Pretty much x and y turns into y and x. Negative 5, 2 turns into 2, negative 5. Negative 1, 4 turns into 4, negative 1. Let's do some more examples. You have quadrilateral JKLM, which again, I've already got graphed, makes it a whole lot quicker. Does everybody know what a trapezoid is? Is that a trapezoid? I know this is completely off subject. What's special about trapezoids? One set of parallel lines. Correct? Is that trapezoid? How could we, and this is getting way ahead of myself, back next, when we get to like chapter 5, we do a lot of this. But I want to show you that what we're doing in this chapter applies to chapter 5. How could I see if this is a trapezoid? And a lot of people are going to say, well, it looks like one, so it is one. No. Sorry, that's second grade. We're in 10th grade now, so we're gonna determine if this is a trapezoid by using other means. We've got to see if these are parallel. How do you see if they're parallel? Slope. Rise over run. From this dot to this dot. Like I said, I'm off task, but that's okay. 1, 2, 3, 4, 5, 6, 1, 2. What's rise 6, run 2? What's the slope? 3. Rise 6, run 2. 6 over 2 is 3. From this dot to this dot. We rise 1, 2, 3, 4, and we run 1. So it's 4. Is that a trapezoid? No. Does it look like a trapezoid? Yes. 3 and 4, slopes of 3, slopes of 4, those are pretty close. So they're going to look parallel, but it is not parallel. But anyway, we want to translate this, or excuse me, we want to reflect this. 2, 2, 4, 1, 3, negative 3, and 0, negative 4. We want to reflect it across this y equals x. Rise 1, run 1, rise 1, run 1. We want to reflect it across that line. And honestly, Vanessa, this rule is pretty easy. So I want you to do all 4 of them. XY is going to turn into YX. So Vanessa, 2, 2 is going to turn into, same thing. 4, 1 turns into, good. 3, negative 3. And 0, negative 4. You just switch your x and y. 2, 2. His nose is on the mirror. 1, 4. Negative 3, 3. And negative 4, 0. Connect our dots. And we have a mirror image. So when we're dealing with reflections, there's our 3 rules. We've already written them down. Reflect across the x-axis, xy turns into x negative y, y-axis, xy turns into negative xy, and reflection across the line y equals x, then xy turns into yx. Problem. And this is a good challenge problem. I want you to try on your own. Let me give you a second to think about it. It says 2 houses are located on a rural road, as shown to the right. You want to place a telephone pole at some point C so that the length of, we're putting a telephone pole somewhere on the road. And we want to place it to where we use the least amount of telephone wire, if that makes sense, or the least amount of wire. Let me go a little bit more extreme though. Let's put A right on the road. Let's do a little bit different on the problem. And let's put B way off the road. House A and house B. And I want to place a telephone pole somewhere. And again, our dilemma is, okay, do we place it here and run a wire here and a wire here? Do we place it here, run a wire here, wire here? Do we place it here, here? Where do we place that telephone pole? Somewhere on the road to where we use the least wire possible. See if this makes sense. I want to place a telephone pole somewhere along this road where it's the same, or we use the least amount of wire possible. Here's your thought. What you do is you take either house A, house B, or you can take actually both of them. It doesn't matter. And you reflect it across the road. Reflect it across the road. So the way that you reflect, we want this distance to be the exact same distance on the other side. Is that pretty close? Is that right there? And that's my reflection. If this is A, this is A prime. Okay, now my next question is, if you wanted to run wire, okay, you wanted to put a telephone pole now, somewhere along this road, ignore house A. Let's say one house is on one side of the road and another house is on the other side of the road. Think about it now. Should you place your telephone pole here and run wire from here to here and then wire from here to here? Is that going to be the least amount of wire that you're going to use? Should you put it, now again, the other person's strategy that I talked to is they wanted to take and measure the distance from A over to B. Let me draw that line there also. Pretty close. They wanted to take and measure the distance from A, where A was at on the road, to B, and they wanted to put it right in the middle. That might be pretty close, but if you're going to run wire from here to here, and then you're going to run wire from here to here, there's a shorter way. The shortest distance between 2 points is a what? It's a straight line. So if you want to use the least amount of wire possible, my line, so the best way of doing it is let's run a straight line. Right? And let's put the pole here. But you're saying, but that's not where the house is. The house is not here, it's over here. So then my question is it not going to take the same amount of wire to go from here to here as it does from here to here? Ain't that the same wire? And you want to use the least amount of wire, so what do? You reflect the house across the road, you connect the two houses, wherever that line crosses the road, that's where that telephone needs to be. Now, is it directly in between those two houses? No. It's closer to house A than it actually is to house B. Translations. A translation or a slide. Here's what your rules are going to look like now. XY turns into something like x plus 4, y minus 2. And that's actually the transformation that is mapped up here. Show you how to do this. If you had a point like -1, 1, which is actually right here, and you use this transformation to map it, is the word that people use, map it onto its image. This is a pre-image, and we're going to map it onto its image under this rule. X turns into x plus 4. What does that mean? Take x and you add 4 to it. That's it. -1 turns into -1 plus 4 or 3. Y turns into y minus 2. So 1 turns into 1 minus 2 or -1. So what used to be at -1, 1 is now at 3, -1. Now let's talk about, do you see how that translated it slid it over? There's a connection between this and what you did on the circles. But unfortunately at the same time, there might be some confusions between this and what we did on the circles. Because look what this did. X plus 4 moved your point from -1 over to 3. And the y minus 2 moved it from +1 down to -1. So this plus 4 moved it right 4, and this minus 2 moved it down 2, which is exactly what you would think it would do. Plus 4 moves it over right 4, minus 2 moves it down 2. And like I said, that's one of the main reasons I put it in this chapter with the circle stuff, so that we can keep them separate. Because if this had been circle stuff, it does backwards what you would think it would do. Now, if you're talking about transformations, plus 4 on the x does exactly. Moves it right 4, down 2 on the y, moves it down 2. Just like it says it would. Next one. It says find the image of triangle XYZ. Let me move the whole thing. You got triangle XYZ with point X being at 2, 1. And sometimes they'll do this. They won't give you the points. You'll have to pull them off yourself. 3, 3 is Y. And -1, 3 is Z. And we want to transform them under this rule. XY is going to turn into X minus 2, Y minus 5. Do you know where that's going to move that? X minus 2, left 2. Y minus 5, down 5. So here we go. -1, 3. 3, 3. And 2, 1. Will turn into Carson, help me with the first one. -1, 3. X minus 2, go ahead. And 3 minus 5, -3, -2. Very good. 3-3, Sierra, turns into, perfect. And finally, Rachel, 2-1, turns into 0, -4. Good. And I've already got a graph. Wow, in the same color, that's pretty good. So you've got 0, -4, which is here. It moved this point left 2, down 5. It moved this point left 2 and down 5 to -3, -2. And it moved this point left 2 and down 5 to 0, 1, -2. That makes sense. Okay, finally rotation. A rotation about a fixed point called the center rotation. Okay, I discussed that a little bit a while ago. If you want to rotate an image around a fixed point, that fixed point is the center of rotation. I want you to think of it like this. There's strings attached. And as you rotate it around that center of rotation, let's say we want to rotate it 90, 180, 270, 60, 50. We want to rotate it some amount of degrees. Because anytime you're spinning, you're talking about degrees. That is your angle of rotation. If a point is not the center of rotation, the image and pre-image are the same distance from the center of rotation, and the measure of the angle of rotation formed by the pre-image and the center of rotation. So pretty much what it's saying is, whatever angle you're going to spin this. Okay, let's say that you want to spin it 90 degrees clockwise. 90 degrees clockwise. Clocks go this way, right? So you would take from here, okay, you would measure 90 degrees, you would form a 90-degree angle with this, and that's where you would rotate that to. Same way here, you want to rotate that 90 degrees, you draw a 90-degree angle, and that's where it would rotate it to. The distance, if you have that center of rotation, again, the leash, the string, remains the same distance from that center of rotation. It's not going to be further. The dog that's running around that stick or running around that pivot point, its leash stays tight. Think of it like that. As you spin, your leash stays tight. Here's an example. Here's point C, which is your center of rotation. A prime is the image. A prime is the image of A after a 120-degree rotation. So here's A. Notice the tight leash. It spins 120 degrees. That's your angle of rotation. And you now are at A prime. And notice you have that same tight leash. The distance from C to A is the same as the distance from C to A prime. Keep a tight leash. I don't think we're going to do these. I want to skip over and get to these. Here's your rules for rotations. And notice that each of these rotations are in a counterclockwise CCW, or in a counterclockwise direction. And we'll talk about it here in a second. Well, how in the world do you go in a clockwise direction? Here's your rules. A 90-degree rotation, and again, you might want to put CCW, counterclockwise. Your rule is XY turns into -YX. A 180-degree rotation. XY turns into -X, -Y. And a 270-degree rotation, counterclockwise. All three of those are CCW, counterclockwise. XY turns into Y, -X. Next problem. Triangle PQR has vertices at 1, 1, 4, 5, 5, 1. Graph triangle PQR and its image after a rotation of 90 degrees about the origin. If it doesn't say, we're going to assume, since all it gave us was counterclockwise, we're going to assume here that we're rotating counterclockwise. And I think a big reason for that is, think about when you're graphing. Doesn't your quadrants go counterclockwise? I think that's probably the reason that most of the time when we're rotating, we're talking about a counterclockwise rotation. Let's see what I've got. No, don't need that yet. So let's graph it. Actually, let's just throw that in the garbage and do it all our own. Give me some graph paper. Here's some. So we have the triangle 1, 1, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5, and 5, 1. 1, 2, 3, 4, 5, 1. Triangle PQR. Now we want to perform a transformation. XY turns into, okay, 90-degree rotation about the origin. I forgot to point that out a while ago. The center of rotation for the ones that you just wrote down are all about the origin. So what's the rule? XY turns into negative Y, X. Is that right? So the point 1, 1 turns into what, Kyle? Now this is a tough one, right? Notice what our rule says. XY turns into negative YX. So pretty much whatever Y is, you're going to have to put where the X is. Whatever X is, you're going to put where the Y is, right? And then you're going to make whatever the Y number is negative. So you're going to flip-flop the two and make the Y negative. So what did you get, Kyle? I think you said negative 1, 1. Good job. 4, 5 turns into, Nicole, try this one for me. We're going to flip-flop and make the Y negative. What do you get? Perfect. And 5, 1 turns into what, Abby? Perfect. And let's test it. Let's graph them and see. Negative 1, 1. Y'all watch this. Connect them. And just test it. If I drew a line there and I drew a line there, that's a leash. Okay, I've got this point on a leash, and I've got this point. We're going to rotate this point on the leash 90 degrees, and we're going to keep that leash tight. Is that a 90-degree rotation? Yes. Let's do the same thing with our other points. We've got the point 4, 5 turned into negative 5, 4. 1, 2, 3, 4, 5. 1, 2, 3, negative 5, 4. And you can do the exact same thing with the leash if you wanted to. You could draw a line from 4, 5. Well, actually, it's kind of the same line, isn't it? Because this is in a straight line with this point. This is in a straight line with this point. So yeah, you got the same thing going on. You have a right angle. And the last one's at negative 1, 1, 2, 3, 4, 5. And you can test that. Draw a line to here, draw a line to here, and you're going to have a right angle. There, there, there. You took that triangle and you rotated it 90 degrees about the origin. It's an isometry, reminder, because the three side lengths, nothing's different. You can measure this side, you rotate it at 90, it's now here. You can measure this side, you rotate it at 90, it's now here. You rotated this side, rotated at 90, it's now here. The three side lengths are the same. It is an isometry. Maybe one more, and then we'll talk a little bit about clockwise rotations. There's your 4 points. Your 4 points were 2, 1, 6, negative 3. Oops, skipped 1, 7, 1, and 1, negative 3. The rule is we're rotating 180 degrees. So what does XY turn into? Is it negative X, negative Y? That's easy. All right. I'm not even going to write them down. Watch this. 2, 1 is going to turn into what? Negative 2, negative 1. And that is a rotation. Again, leash, spin it 180 degrees, tight leash. Yeah, looks good. 6, negative 3 turns into 1, 2, 3, 4. Yeah, negative 6. 1, 2, 3, 4, 5. Negative 6, positive 3. 6, -3, notice the straight line. 7, 1 turns into -7, -1. 1, -3 turns into -1, +3. You rotated 180 degrees, and you got to be careful with what this. Let's see. This point is actually rotated up to here. Okay, that's your 180 degree rotation. Okay, rotated every point 180 degrees about the origin. So last thing that we need to discuss. Let me make sure. Yeah. Last thing we need to discuss this, we talked about counterclockwise rotations. We took things and spun them, let's say it was here. Lee. I want to spin it 90 degrees. I want to keep the same distance. I measure the distance from here to here. This is about right there. Okay. We spun things 90 degrees counterclockwise. Well, how do you spin things clockwise? How do I spin this from here 90 degrees this direction? Any ideas? Think about this. If you're facing, that's your eyeballs. There's your nose. You're facing that direction. Okay. You're facing this direction, and I tell you to spin 90 degrees in a clockwise rotation. You're going to spin from there to here. Correct? You spun 90 degrees clockwise. What if I asked you to spin 270 degrees counterclockwise? Think about it. Where do you end up? The same place. So the ones that we had, the rules that we had were for counterclockwise rotations. Well, guys, 90 degrees clockwise is the exact same thing as 270 degrees. So 360 is a full spin. 90 clockwise, 270 counterclockwise is the same place. 90 counterclockwise and 270 clockwise is the same place. What about the 180s? If I tell you to spin 180 one way or 180 the other way, it's the same thing. Let's say it's spin halfway around to the left or halfway around to the right, you end up in the same place. So if I ask you to do a 90 degrees clockwise rotation, you don't have a rule for that. The way that you perform this, you would do a 270 degrees counterclockwise, and you end up in the same answer. If I ask you for a 270 clockwise rotation, you would do a 90 counterclockwise. If I ask you for a 180 clockwise, honestly, that's crazy. 180 clockwise, counterclockwise, it's the same thing. I don't have to give you directions on a 180 degree spin. That's like saying, I want you to spin around 360 degrees counterclockwise. Well, if you spin 360, you end up in the same place anyway. It doesn't matter what way you spin, it's the same. We'll talk about terminal side later. But that's how you do clockwise versus counterclockwise.